The information presented in this video is meant to help students interpret infrared spectra at the level of Organic Chemistry 351 lab. Infrared spectroscopy is one of the fastest methods for determining information about the molecular structure on a wide variety of compounds. It is especially useful in determining the presence of a variety of functional groups that may be contained in a given compound. IR spectroscopy relies on the absorption of light in the IR region of the electromagnetic spectrum. IR photon absorption values are most often reported in units of wave numbers, or reciprocal centimeters, which can be converted to photon wavelength by raising the value to the -1 power. A typical organic chemistry IR spectrum covers a range from 400 reciprocal centimeters to 4,000 reciprocal centimeters. There are a number of vibrations that can be analyzed by IR spectroscopy. With IR spectroscopy, we are looking at atomic vibrational motions. IR light energy absorbed by organic compounds does not have enough energy to cause electrons to jump orbitals. It just causes vibrational motion, such as symmetric bond stretching, asymmetric bond stretching, symmetric bending, and asymmetric bond bending, as examples. IR spectroscopy exploits the fact that molecules have specific frequencies at which they rotate or vibrate. When a beam of IR light is directed at a sample, some of the photons are absorbed by the molecule as the molecule undergoes a specific vibrational movement. The remaining photons pass through the molecule and strike a detector. The detector sends a signal to the computer, which interprets the data and generates a spectrum. The spectrum is a graphical representation showing which photons were absorbed or transmitted, those that were not absorbed, by the compound. Because different functional groups create distinct absorption bands, the spectrum can be interpreted to determine the functional group composition of the compound. There are two regions of interest in the IR. There is the functional group region, which provides information about the types of functional groups in a particular molecule. This region is usually those with higher wave numbers, greater than 1,500 reciprocal centimeters. And those in the fingerprint region provide structural information about a molecule, but this is a difficult region to interpret and is often referred to as the forest of lost chemists, simply because of the many peaks resulting from the variations of the bending vibrations. Peaks in this region are very often hard to interpret and are not useful at this level. The region that we are going to be interested in looking at, as I mentioned earlier, will be the functional group region. And there are three distinct groups of interest to us in this region. There are those that are single bond stretchings, triple bond stretchings, and double bond stretchings. We will focus in on these areas. Occasionally, I will mention some areas in the fingerprint region, though these are often difficult to find in relation to the other peaks in this region. When interpreting an IR spectrum, you will need to look for evidence of all the functional groups that are present and all that are not present. Often IR spectra will be used with other types of spectroscopy to determine more complex molecule structures. In this class, you will only focus on IR spectroscopy with simple samples. In the following slides, I will refer to the different bands that you should observe for different functional groups, and I will have examples of each of these. This is the table I will refer to as I go through the PowerPoint presentation. I have here examples of the functional groups encountered in organic chemistry. If a particular functional group is encountered in a molecule, you should observe all of the bands, with a few exceptions, for that functional group if it is actually present in a molecule. Again, IR spectroscopy will not help you determine the structure of a molecule, but it will help you determine which functional groups are present in a molecule, which will aid in interpretation. To begin with, we are going to look at a simple alkane. Alkanes, as you have been taught in class, have carbon-carbon single bonds and bonds that are single bonds to hydrogen. The carbons in an alkane are sp3 hybridized, and the hybridization of the carbons is very important. In the example of hexane, all of the carbons are sp3 hybridized, and you actually can see some of the stretching and vibrations from the single bonds between the carbons, but they are again in the fingerprint region, so we're not going to focus on those. The ones that we are going to focus on are in the functional group region, which is 1500 and greater. And as you can see, there is a very intense band here just below 3000. The region that we see these carbon-hydrogen sp3 stretches is between 3000 to 2850 in general. And I want to make one other point as we look at spectra, that the intensity of the transmittance isn't actually very important. It's the location of the peak that matters the most. This is an example of an alkene. I've used here as an example 1-pentene. So like hexane, there are still sp3 hybridized carbons with hydrogens bound to them. So the peaks that you saw for the alkane should still be present in the example of this alkene. So those CHs from the sp3 carbon-hydrogen bonds still show up just below 3000 wave numbers. They need to be here because those functional groups are still present in this molecule, so they haven't disappeared. But now we have a new functional group. We have the double bond. And because it is now going to contain sp2 carbon-hydrogen bonds, we should see sp2 carbon-hydrogen stretch. And this shows up usually just above 3000 wave numbers. The actual region is 3010 to 3100 wave numbers. And this peak tends to be a little bit less intense than the sp3 carbon-hydrogens, but that is just usually, is not always true. You will also see a carbon-carbon double bond, and this usually falls just around 16 to 1700 wave numbers. The actual range is 1620 to 1680. Some are more intense than others, but it will show up in this region, and that is due to the carbon-carbon double bond. Sometimes you can get information as to the type of alkene that you are actually looking at. This particular one is a monosubstituted alkene, and the information that you would be looking for would be in the fingerprint region. So this is not something you need to know necessarily for lab, but it may be helpful to some of you if you're struggling with the interpretation. One of the peaks I would be looking for is a terminal double bond stretch, and this shows up usually around 910 to 999, and that would be this peak here, and that would be indicative of the monosubstituted or the terminal alkene right in this region. As with this one, there tends to be another peak in this region from time to time. There are two, one again from 910 to 990 and another one from 885 to 895, and they are sometimes more intense or less intense. You sometimes can also use this region to look at cis disubstituted versus trans disubstituted alkenes. If you have a cis disubstituted alkene, you would be seeing a peak of different intensities around 665 to 730. And if it were a trans alkene, the region would be 960 to 980. If it were a trisubstituted alkene, you would see a peak in the 790 to 840 region. So there are oftentimes other peaks in these regions, and so that's not usually the best way to determine the substitution pattern of the alkene, but it may be somewhat helpful. Now I have an example of a alkyne, and specifically a terminal alkyne. This one still has sp3 carbon hydrogens, and so we still see carbon-hydrogen sp3 stretch just below 3000, since those functional groups still remain. Now, because this is a terminal alkyne, there is a carbon-hydrogen sp stretch, and this will also show up in the single bond region of the IR, and it's showing up here. It's usually a very skinny peak, and it shows up usually right around 3300 wave numbers. And it tends to be strong and sharp, but it's usually skinny, and that can be very helpful when you're trying to identify it relative to some other peaks that do show up in this region. Another peak that would have to show up in conjunction with that one, if it were truly a terminal alkyne, would be the carbon-carbon triple bond. right here. And this usually shows up around 2100 to 2260 wave numbers in the triple bond region. So you'd have to have both of these peaks present if you were dealing with a terminal alkyne. Sometimes, though, your alkyne is somewhere in the middle of a molecule, and we call these internal alkynes. For an example, I have 1-chloro-2-pentyne, and in this particular example, we still have sp3 carbon hydrogens in the molecule. So we still see the carbon-hydrogen sp3 stretch just below 3000 wave numbers. And like our other example, we have a triple bond. And so this carbon-carbon triple bond again shows up where we would expect it, around 21 to 2260 wave numbers. But because this one is in the middle of the molecule, there is no hydrogen bound to one of these sp hybridized carbons. So we do not see a carbon-hydrogen sp stretch in this region because it is not a terminal alkyne. Now sometimes when you have a fairly symmetrical alkyne, you don't see the carbon-carbon triple bond. It is possible that it won't show up even though it is present in the molecule. And this is because it's variable. It's not present in symmetrical alkynes. Now this isn't totally symmetrical, but it is fairly symmetrical, and so you don't really see much of a peak in this region. This is minimal and you might miss it entirely. It's just not significant enough to know for sure that that's a triple bond. But you do see, for sure, those sp3 carbon-hydrogen stretches in this spectrum. Another example of molecules that you may be called upon to recognize and be able to interpret are the aromatic rings, specifically benzene rings. Now, benzene rings will have some other functional groups present in addition to what we need to look for here. So just to be aware, there is still an sp3 hybridized carbon, and there are hydrogens attached to this carbon. So we still see those carbon-hydrogen sp3 stretches just below 3000 wave numbers. They're still going to show up. Now, the aromatic ring, all of the carbons in the ring are sp2 hybridized, and 5 of these carbons in this example have a hydrogen bound to them. So you should still see carbon-hydrogen sp2 stretches, in this case just above 3000, and usually not more so than 3100. So they're just above 3000. 3000 is kind of my line of demarcation. Now, because there is some double bond character in the ring, you do see carbon-carbon double bond in the IR spectra. And again, this is usually around 1620 to 1640 in the spectrum. Now, because this is aromatic, there's some other things that you should be looking for. It has a conjugated pi system, and because it's an aromatic ring, we're going to see what are called the four fingers. They usually show up, but every now and again they don't. So don't freak out if you don't see them distinctly. But this example you do, but they look like four fingers. And this region is usually going to encompass from 1600 to 2000-ish, where you see these four fingers. Now, something else to look for in the fingerprint region, which may be difficult depending on how many other peaks are present in this region, but there are some peaks in the 700 to 800 region that can be very useful for helping you to identify the type of substitution pattern on the ring. Now, this is a monosubstituted ring, meaning there is only one substituent attached to the ring. So there are two peaks that we should observe in this region. The first peak should show up roughly right around 700 wave numbers, and the second one should show up roughly around 750 wave numbers. Now, they may be a little off from those numbers, but you should see two peaks in this region. This is an example of a para-substituted ring, which also can be said to have 1,4 substitution pattern. So just like the monosubstituted aromatic ring, I still have sp3 carbon hydrogens in this molecule. So I still expect to see the carbon hydrogen stretch from the sp3 carbon hydrogen bonds. I still have sp2 hybridized carbons in this ring, and 4 of them still have hydrogens attached to them. So I should still be able to find this carbon hydrogen sp2 stretch just above 3000 wave numbers. And because there is double bond character in the ring, I should still be able to find the carbon-carbon double bond just above 1600 wave numbers. Now, because it is aromatic, again, I'm looking for the four fingers. They're not as defined as in the last example, but they are in the right region, and they're not quite as pretty as the last example, but they are here. Now, because this is a para-substituted ring, there's something very distinct that you should be looking for in the fingerprint region. And this is the peak of interest I'm looking for. In para-substituted molecules, you should see a peak at around 800 wave numbers that's fairly intense. Now, as you can see in this example, there's another little peak off to the side, and that's why this can be confusing. That's not the peak due to the para-substitution, but it is in the fingerprint region, so sometimes things are just a little bit more difficult to identify. This is an example of a meta-substituted aromatic ring. So just as before, we are still seeing the sp3 carbon hydrogen stretches, and they show up again just below 3,000 wave numbers. We still have sp2 hybridized carbons in the ring, and 4 of these carbons have hydrogens attached to them, so we still need to be able to identify the carbon-hydrogen sp2 stretch. And it's still going to have double bond character due to it having these carbon-carbon double bonds in the ring. And this will show up just beyond 1600 wave numbers as the carbon-carbon double bond. We also still see the four-finger region. Again, it's not as defined as the first example, but they are still present. And this is indicative of the aromatic ring. And then again, something to look for in the fingerprint region is going to be between 700 and 800 wave numbers. So for a meta-substituted ring, you should be looking for a peak right around 710 wave numbers, and then another one around 775 wave numbers. And again, these are rough estimates, but there should be 2 peaks in this region. For this reason, because they're not exact numbers, I still to this day struggle with identifying a mono-substituted from a meta-substituted aromatic ring with just IR spectroscopy. You would need to rely on some other types of spectroscopy to nail down the structure of that ring for sure. IR would not be enough to know 100% of the time if it were mono or meta, just because there are 2 regions or 2 peaks in this region that vary a little bit. This is an example of an ortho-substituted aromatic ring. And as before, you still see the carbon-hydrogen sp3 stretches just below 3,000 wave numbers. And we still have sp2 hybridized carbons in the ring, and 4 of those carbons still have hydrogens bound to them, so we still see carbon-hydrogen sp2 stretches just above 3,000. And because there's still double bond character in the ring, we see the carbon-carbon double bond just above 1600 wave numbers. And because it is an aromatic ring, we are looking for the 4 fingers. And again, this is not as defined as the first example, but this is the region I would be looking at. Now, an ortho-substituted ring, which is a 1-2 substitution pattern, we're still looking in the 700 to 800 region of the fingerprint. And for an ortho-substituted ring, you should have 1 peak at around 750. Now, this one does have a nice intense peak in this region. There's also a little peak over here to the side, but this is not due to the aromaticity. So again, because it's the fingerprint region, it can be kind of difficult to nail down which substitution pattern you're dealing with. And I wouldn't rely on it to determine if your ring is mono, ortho, meta, or para-substituted. You will need to look at other types of spectroscopy to nail down the substitution pattern for sure. But it is a good way to get an idea as to what the substitution pattern actually is. Up next are ethers. So ethers still have these sp3 hybridized carbons with hydrogens bound to them, and so we're still seeing the carbon-hydrogen sp3 stretch just below 3,000 wave numbers. And something else that you will be looking for in the ether is the carbon-oxygen single bond. Unfortunately for us, this does fall in the fingerprint region. Something that's usually pretty nice about it, though, is it tends to be kind of wide in its structure, and it's usually around 1,000 to 1,300 wave numbers. It does tend to be kind of intense, and it does tend to be kind of wide, but not always. So sometimes you'll be able to find it, and sometimes you won't. Something that I use as kind of a help to me is the fact that the molecular formulas of ethers do have oxygens in them, and you aren't going to be finding any alcohol stretches or carbonyl stretches, which kind of helps you know that it's not going to be one of those 2 types of groups with the oxygen. And I know I haven't shown this to you yet at this point in the video, but I will. Alcohols and carbonyl stretches are very distinct in the IR. And since I don't see either of those 2 types of signals in this IR, it also helps me to understand that this this would be an ether. This is an example of an alcohol. This is 2-butanol. And like some of our other examples, we're still dealing with sp3 hybridized carbons with hydrogens attached. And these stretches will again be identified just below 3,000 wave numbers. Now, a really useful peak is the OH stretch. So if this is an OH stretch where you're observing hydrogen bonding to a significant degree, it's going to be a very wide peak, and it usually ranges from 3,200 to 3,600 wave numbers. So it tends to be very intense and very broad, and that is indicative of an alcohol that is hydrogen bonding to other groups. Now, the alcohol also has a carbon-oxygen single bond, and so again, in the fingerprint, you may or may not be able to identify this peak. But again, it's going to be in the same region roughly that the ethers are in. This one's usually a little bit more specific. It's about 1050 to 1150, and it tends to be strong and kind of broad as well. This is an example of another type of alcohol. This one is an alcohol that experiences hydrogen bonding with other alcohols to a degree, and it also doesn't hydrogen bond to all adjacent molecules due to the fact that this alcohol is bound to a tertiary carbon. So there's a lot of bulk in the vicinity of the alcohol, and this impedes the alcohol's ability to hydrogen bond to some degree to other alcohols. So there are two alcohol stretches you may or may not see in different molecules. So this one, you do see the OH bond due to hydrogen bonding interactions with adjacent alcohols. And you also see an OH bond here, right around 35 to 3,700 wave numbers, which is usually very sharp and strong, which is due to the alcohol not hydrogen bonding to other adjacent alcohol functional groups. And like our other examples, we are still dealing with sp3 hybridized carbons that have hydrogens attached to them. So we see the carbon-hydrogen sp3 stretch just below 3,000 wave numbers. And in this case, we still have the carbon-oxygen single bond down here in the fingerprint region. Okay, this is an example of an amine, and like some of our other examples, this is an aromatic ring. So we're going to see some of the same peaks here that we saw with our previous examples. So I'm going to focus in first off on the peaks you should see due to the aromaticity of this molecule. So because it is an aromatic ring, we are dealing with sp2 hybridized carbons, and 5 of those carbons have hydrogens attached to them. So these are sp2 carbon hydrogens, and they should show up just above 3,000 wave numbers, and they are here. Because it is an aromatic ring, as before, we are dealing with carbon-carbon double bond character, and we see this signal just about above 1,600 wave numbers. And because again it's aromatic, we are looking for the 4 fingers to designate that this is a benzene ring, and you do see them pretty well here in this instance. And it's also a monosubstituted aromatic ring, meaning there's only one substituent coming off of the ring. So in the 700 to 800 region, you see we do have a peak just below 700 and another peak really close to about 750 in this region. So that's indicative of the monosubstituted aromatic ring. And I've discussed all of that with you previously. Now, this happens to be an amine, specifically a primary amine. And what it means to be a primary amine is that the nitrogen is attached to only one carbon substituent. The other 2 bonds the nitrogen has are 2 hydrogens. So these single bonds can be detected in the single bond region, and they are hydrogen bond capable. So they're in the same region as the alcohol, but they do look a little different. You will see 2 bands here because there are 2 NH bonds for a primary amine. And so that's very indicative of the primary amine, the fact that there are 2 peaks. Again, remember with the alcohol, there was only 1 peak in this region. But with the primary amine, there are 2 bands because there are 2 bonds to hydrogen with this nitrogen. There is also a carbon-nitrogen single bond, and it's going to be typically in this region right in here. But again, there's a lot of peaks in this area, so we're not going to try and identify it. This is an example of a secondary amine. I wanted to show you a secondary amine so you can see the differences between the secondary amine and the primary amine I just showed you. So let me go through the peaks that aren't in relation to the amine first. So first off, I have an sp3 hybridized carbon with hydrogens attached. So as before, this peak for these bonds should show up just below 3000 wave numbers, and those are for the carbon-hydrogen sp3s. This is also going to contain sp2 hybridized carbons, and 5 of these carbons have hydrogens attached to them, so they show up just above 3000 wave numbers. And because this is an aromatic ring, we're still going to see the carbon-carbon double bond of the ring just above 1600 wave numbers. And because it is an aromatic ring and specifically a benzene ring, we are looking for the 4 fingers. And in this case, we're dealing with a monosubstituted aromatic ring. So in this 700 to 800 region, again, I'm looking for a peak around 700 and another one right around 750 to designate that that's monosubstituted. Now this does happen to be an amine, and it's a secondary amine, meaning that the nitrogen is bound to 2 carbons. They don't have to both be sp3 or sp2, they can be one of each or both the same, it doesn't really matter, but the point is that there are 2 carbons bound to the nitrogen and only 1 hydrogen. So you do still have an NH bond, and NH bonds are still hydrogen bond capable. And they're going to show up in the same region as the primary amine and the alcohol. The difference is, though, that this time you only have 1 NH bond, so you only have 1 NH peak. So that's why there's only 1 band. Whereas in the previous example, there were 2 in this region because there were 2 hydrogens attached to the nitrogen. That's the big difference here. And again, if you really want to go looking for it, the carbon-nitrogen single bond, but again, look how many peaks are in this region. That's getting really hard to interpret. So I don't usually try and go and find that bond. Okay, up next is an example of a tertiary amine. And as you can see here, this nitrogen has 3 carbons bound to it. There are no hydrogens bound to it, so it's going to look different than the secondary or the primary amine. So again, I'm going to identify the peaks that are not in relation to the amine first. So as you can see in this particular example, there are sp3 carbon-hydrogen bonds that should be present in the IR spectra. And again, they're showing up just below 3000 wave numbers. There is also sp2 hybridized carbons, and 5 of them have hydrogens bound to them. So these carbon-hydrogen sp2 bonds should show up just above 3000 wave numbers. This ring also has some double bond character between the carbons, and so the carbon-carbon double bond shows up again just around 1600 wave numbers. And because it is an aromatic ring, we're still looking for the 4 fingers. And because it's still a monosubstituted aromatic ring, we are looking for a peak at 700 and 750 in the fingerprint region. Now this nitrogen doesn't have any hydrogens bound to it. That's very important, so it's not hydrogen bond capable. And because of that, when you look in this region for the NH bonds, you don't see any because there aren't any on the nitrogen. And that's kind of helpful to be aware of. So as you look at the molecular formula and realize there's a nitrogen, there's a high probability that it might be an amine. And you can tell what kind of an amine it is again from the IR. I'm going back a few slides. So again, if it were a primary amine, you would be seeing the 2 NH peaks for the 2 NH bonds. If it's a secondary amine, meaning there's 1 hydrogen bound to the nitrogen, you'd be seeing 1 peak in this region. And if it's a tertiary amine, there are no hydrogens bound to the nitrogen, so there are no peaks in this region. So that should help you determine the degree of substitution on a nitrogen if you look at the IR spectra. Another compound that contains a nitrogen is something called a nitrile. So this is going to have an index of hydrogen deficiency because of the triple bond between the carbon and the nitrogen. So as you see here, there are no NH peaks because there aren't any NH bonds, but there is this triple bond, and it shows up in the same region as the alkynes, and it shows up right here. It's going to usually show up around 2210 to 2260, and I really couldn't identify this as an alkyne or a nitrile alone. Again, I'm going to rely probably on the molecular formula and some other types of spectroscopy to be 100% sure. But this is for sure a triple bond. And since there is nothing else really for the nitrogen to be doing, the good bet is that it's a nitrile. You've also got your sp3 carbon-hydrogen bonds that you should be observing. and you do just below 3,000. And because this is an alkene, we do see the carbon-hydrogen sp2 stretches just above 3,000, and we still see the carbon-carbon double bond just above 1,600 wave numbers. Now this particular one is a trans-alkene, and so there is a peak that you should be looking for between 960 and 980 here. But again, as you can see, these peaks are really hard to look at in the fingerprint region, so it's really hard to distinguish that you're dealing with the trans-alkene from that information. There's just too many peaks in that region to be truly helpful to you. This is an example of a nitro group. This is another way that you might have nitrogens and oxygens in your molecule. This particular example is nitrobenzene. And again, I want to talk about the aromatic ring before I talk about the nitro group. So with the aromatic ring, we are again dealing with sp2 hybridized carbons, and 5 of these carbons have hydrogens attached. So we should be seeing sp2 carbon-hydrogen stretches just above 3,000 wave numbers, which we do. Now, I know this peak is in the region of sp3 carbon hydrogens, but you don't have any. Sometimes you see some peaks that don't correlate to a functional group in your molecule. This does have, though, carbon-carbon double bond, and we are dealing with an aromatic ring, so we're seeing 4 fingers very significantly here. And this particular one is a mono-substituted ring. It's a little harder to tell in this region that that's what we're dealing with. The peaks aren't as defined, but we do have one right around 700. I know there's another one off to the side, and this one is not quite at 750. So this would be a lot harder to identify as a mono-substituted aromatic ring from the IR. But you would be, again, dealing with other types of spectroscopy if you were trying to nail down the structure. Now the nitro group, there are some very distinct peaks to look for. There are 2 of them, and one of them will be at about 1515 to 1560, and the other one will be about 1345 to 1385, and they tend to be 2 strong bands of relatively equal intensity. But that's what you're going to be seeing if you're dealing with a nitro group. This is an example of an alkyl halide. Now, halides don't show up very well at all in IR spectroscopy. In fact, with older IRs, and depending on what kind of IR spectroscopy you want to do, you may still be using this method. They used to use salt plates or make pellets with potassium bromide because the halogens just don't show up very well in the infrared region. And so they know that if that's what they're sandwiching compounds between, salt plates are using potassium bromide to make a pellet to put in the IR beam, you're not going to have much interference from the halogen present. So this is the different locations. These are the different locations for the different carbon-halogen bonds. In this particular example, I have a carbon-bromine bond, and they're down here. This one's at between 500 to 600 wave numbers, and there's usually a lot of other stuff in this region. It's hard to pick them out, so we usually don't try to find this band at all. But something you will see intensely in the functional group region are the sp3 carbon-hydrogen bonds, again just below 3,000 for this particular example. So again, don't try to identify halogens too much with IR. You want to use a different type of spectroscopy to verify the location of a halogen. This is an example of a ketone. Ketones have what is called the carbonyl group. What a carbonyl group is a carbon-oxygen double bond. And these usually are very intense bands, and they show up just above 1700 wave numbers. So I have many students that get confused between the carbon-oxygen double bond and the carbon-carbon double bond. Remember that the double bond shows up between 16 to 17. It's a little bit lower. The carbon-oxygen double bond is a little higher than 1700, so you really need to know where that 1700 number marker is. If it's above 1700 wave numbers, it's most likely due to the carbon-oxygen double bond. And I will also tell you that this bond tends to be more intense than the carbon-carbon double bond. I can't say it always, but it does tend to be more intense. It also tends to be the most intense band in an IR spectra when it is present. Now, in this particular example, be aware that there's also carbon-hydrogen sp3 bonds, and again, we see those just below 3,000 wave numbers. There are many different compounds that have these carbon-oxygen double bonds, and you want to be able to identify one from another. A group that often gets confused with the ketone is the aldehyde, but there are things to look for in the IR to help you know if you're dealing with a ketone or an aldehyde. So again, we are looking for that carbon-oxygen double bond, and it's going to show up usually again just above 1700 wave numbers, just like it did with the ketone. It's in the same location. The big difference though with the aldehyde is the fact that on one side of the carbonyl group is a hydrogen, and this hydrogen is bound to the sp2 hybridized carbon. Now this carbon-hydrogen sp2 bond shows up in a totally different location than that experienced previously by the alkenes and the aromatics. This one has its own unique location. So this carbon-hydrogen bond shows up here. There's actually two peaks, and you'll need to pay attention to the wave numbers. So one of them is at 2820 to 2850, and the other is at 2720 to 2750. But there's usually two bands here of medium height. And again, I'm going to go back to the ketone. Notice for the ketone, there's nothing in this location because there is not a bond to hydrogen coming off of this carbon that is bound to the oxygen. So that's the big difference that you're looking for to identify an aldehyde from a ketone. And again, just to mention it, these are carbon-hydrogen sp3 stretches that we do absorb just below 3000 yet again. This is an example of an ester. It also contains the carbon-oxygen double bond. And like the ketone and the aldehyde, it shows up just above 1700 wave numbers as a very intense peak. Now, the ester is going to have some other peaks that you may want to identify. In this particular case, they're always going to be in the fingerprint region, and so they may or may not be something that you can identify from other peaks. But we are going to be looking for these carbon-oxygen single bonds, just like we were looking for them with the ethers and the alcohols. So in this case, there is a carbon-oxygen sp2 and there is a carbon-oxygen sp3. So you may see two bands or more in this region between 10,000 to 1,300. And in this case, we do have those two bands. They tend to be fairly intense and kind of broader peaks, but that's where those two carbon-oxygen peaks are located. And we also have in this case, yet again, those carbon-hydrogen sp3 stretches just below 3,000 wave numbers. Up next is a carboxylic acid. So again, this has that carbon-oxygen double bond, and again it's going to show up around 1700 wave numbers or just above it as a very fat peak. This also has an alcohol, but this alcohol looks extremely different from the alcohol I showed you before because this alcohol is bound to the sp2 hybridized carbon of a carboxylic acid. This unit works together as a whole. There's actually some resonance structures that can be drawn that we're not going to talk about in this video, but it does affect what the alcohol looks like and where it is. Normal alcohols, as you remember, were those broad peaks right in this region. What you're going to find with the carboxylic acids is that the alcohol peak shifts over and it usually moves on top of the carbon-hydrogen stretches. And it may be kind of like this, or else it might be kind of jagged, but it will be in this region and it takes up a lot of space in the IR. It usually goes from about 3,300 wave numbers all the way to 2,500 wave numbers. So it's really broad, and it typically falls right on top of your carbon-hydrogen stretches. So you may not even see them popping out here at the end. In this particular case, I do. I still see those carbon-hydrogen sp3 stretches popping out down here. But you may not be able to see them at all because this peak will be on top of them. Just something to be aware of. You've also got carbon-oxygen single bond, right around 1210 to 1320, and they're usually still broad, but it again may be difficult to identify this peak because it's in the fingerprint, so don't freak out if you can't find that peak. Up next is the acid anhydride. Like the other carbonyl compounds, we still have these carbon-oxygen double bonds. This one's kind of unique though, because you're actually going to see two carbon-oxygen double bonds right next to each other. There are two peaks here. One is around 1830 to 1800, and the other is around 1740 to 1775. So that's kind of a very unique feature of the acid anhydride that is the dead giveaway that you're dealing with something like this. You're also going to be looking for that carbon-oxygen single bond in the fingerprint region, which may or may not be real visible to you. And again, it shows up usually around 10 to 13-ish hundred wave numbers, but it's usually pretty intense. This one you should be able to see carbon-hydrogen sp3s, but they're almost non-existent. they are still below 3,000. And so just because, again, like you should expect to see it, doesn't mean you're going to see it. Intensity isn't always there. Intensities vary, so don't worry too much if that transmittance intensity is less than what you expect it to be. Okay, up next is an amide, and we are going to look at benzamide. Like some of our other compounds, this is still an aromatic ring, so I want to talk about that aromatic ring again just to make sure you remember where all the peaks are. We are dealing with sp2 hybridized carbons. 5 of them have hydrogens attached to them. So we're still trying to look for that sp2 carbon hydrogen region. I really don't see it well defined here at all. I'd probably miss it if I were a student because it's just not well defined. But you do see the carbon-carbon double bond right here. And again, I'm looking at 1600 as my point of interest here that I'm looking for, but you see it right there. And then I'm not really seeing the 4 fingers in this case, but that doesn't mean it's not aromatic just because I'm not seeing it. And I'm looking for the fact that this is monosubstituted in that 700 to 800 region, and we do see 2 peaks in this region around 700 and 750. Again, the intensity isn't as great as some of the others. It's a little harder to pick out in this particular example that you're dealing with an aromatic ring. It's in fact quite a bit more difficult. Something though that you want to look for with the amide, regardless of whether or not it's attached to an aromatic ring, is the carbon-oxygen double bond. And again, this one is going to show up right around 1700 wave numbers, but in the case of the amide, it's a little bit lower than that. It's going to be around 1640 to 1690. So it is a little bit lower than you would typically expect, and that's due to some of the resonance issues we're dealing with here. There is a nitrogen in this case with 2 hydrogens attached, and you are still going to see those 2 NH bonds like we did with the primary amine in this region down here. If it were an amide with only 1 hydrogen in this region, you would only see the 1 peak, and if it were an amide with just carbons attached to it in this region, you wouldn't see these peaks at all, just kind of like you did with the amines. So here's an example of a substituted amide. So this one has a carbon coming off of the nitrogen. So again, we'll talk about it. So the aromatic ring, we are dealing with sp2 hybridized carbons, and there are hydrogens attached to these carbons, and we see those stretches just above 3000 wave numbers. We also see the carbon-carbon double bond. This is a little lower than 1600. The amides tend to move things over to the right just a little bit, and we do see the 4 fingers. And in this case, it's monosubstituted. I'm not really able to tell that extremely well from this signal. Again, we would be hoping for 2 peaks at 700 and 750, and that's kind of hard to tell exactly what we're dealing with in this region. You're still dealing with that carbon-oxygen double bond, and because it's an amide, it is a little bit lower than 1700 wave numbers. It's going to be 1640 to 1690, and this nitrogen has 1 hydrogen attached to it, so you're going to see 1 NH peak in this 31 to 3500 wave number region. And then we still have, in this case, an sp3 hybridized carbon with hydrogens attached, and so we see those carbon-hydrogen stretches just below 3000. And lastly, here's an example of an amide that doesn't have any hydrogens attached to the nitrogen. So let's talk about the aromatic ring first. So again, we have sp2 hybridized carbons of the ring, and 5 of these carbons have hydrogens attached to them. Because they're sp2 hybridized carbon-hydrogen stretches, they should show up just above 3000 wave numbers. I don't know if I were a student that I would be able to recognize that. It's kind of undefined looking. But some things that are kind of helpful, you're looking for the carbon-carbon double bond, and here it is just below 1600 wave numbers. And the 4 fingers are very distinct in this case, which is kind of nice. It's a monosubstituted ring, but again, I can't really tell that is monosubstituted very easily in the fingerprint region. There's 3 peaks in this region. In this case, there's another signal in this area because it is the fingerprint region. So it gets kind of hard when you're dealing with the fingerprint region. Something that is very defined is the carbon-oxygen double bond of the amide right here. And again, here's 1700, here's 1600. It's in that region in between because it's an amide. It's in that 1640 to 1690 region. They just tend to be a little bit more to the right. In this case, again, we've got our carbon-hydrogen sp3 stretches, and they show up very distinctly right here below 3000. So sometimes you see peaks that are very distinct and other times you don't. So I don't always try to make things up if I'm not sure. In this particular case, the things that I would be sure of, because it isn't that distinct, is I would be for sure there are carbon hydrogen sp3s. I would be for sure that there's an aromatic ring, and I'd be for sure that there's a carbon oxygen double bond. Those are probably the most distinct peaks in the spectra that help me know what I'm looking for.